Continuing with the previous lecture, we'll now go from matching kernels to matching kernels for image pyramids. For example, having a multi-resolution pyramid of images and being able to use that idea to develop matching kernels. The slides are once again borrowed from the lectures of Professor Avritis at Indria Ren. Descriptor matching, as we just saw in the earlier lecture, can be given by you have XC and similar YC for the features that belong to a particular visual word in images X and image Y. Then a matching kernel for something like bag of words could be given by summation over the same cluster centroids, just counting the number of features belonging to it. You could also include some weighting factor for each of these summations if required. And a more general form that we saw last time was what you see below here, which is k of x comma y is equal to gamma of x into gamma of y, normalization functions, into a summation over all the codebook elements. WC is a weight that we are introducing, which we can choose to use or not, and m of xc by c, where m is the matching function. Now we'll talk about going beyond single level matching and matching at the level of pyramids, and we'll describe a seminal work in this context known as pyramid match kernels. So pyramid matching is an efficient method that maps unordered feature sets, which is what each image is. Each image is an unordered set of features. We're going to convert that into multi-resolution histograms and then do matching using weighted multi-resolution histograms. So we ideally can start with the finest resolution histogram cell where a matched pair first appears, and then we keep merging histograms as we go up the pyramid in this particular context. And the work has a very nice interpretation where it can be shown that it approximates a similarity in a partial matching setting, where if you had only a partial set of features in one image, match a set of features in another image, pyramid match kernel approximates that optimal partial matching between those two images. For more details, I would also recommend you to read this paper called Pyramid Match Kernel. It's written very well and explains some of these ideas in detail if you're interested in knowing more. Let's start with defining our histogram intersection, because we're going to define histograms in both images. Obviously, we're going to define them at multiple levels, but let's first talk about how do you match histograms in this context. So if you had two histograms X and Y of B bins each, so let's say this is X and this is Y, both are histograms with B bins each, we define the histogram intersection as minimum of Xi, Yi, one element of the histogram, in both of these images, and sum these up over all the B bins. Right? So you take the first bin of histogram, the first bin of the second one, take the minimum value of the next bin in the histogram, and add them all up. That's what we define as the histogram intersection. Interestingly, you can show that this notion of histogram intersection, which we define as kappa sub hi, has a relation to L1 distance. We are not going to prove it here, but probably leave it as an exercise for you to look at. You can see that the L1 distance between two vectors X and Y can be given by L1 norm of X plus L1 norm of Y minus 2 times the histogram intersection. Okay, try it out for yourself. Take a couple of examples of X and Y. You'll actually see that it holds in practice. Please try proving this also if you can. This is an interesting exercise for you to work out, but you can show that this histogram distance is related to the L1 distance. Remember, L1 distance is the sum of absolute values of that vector. Let's come back to the pyramid match kernel now. So we said that the pyramid match kernel does a weighted sum of histogram intersections at different levels of two images, and it approximates optimal pairwise matching. So we'll first conceptually talk about it, and then we'll give a concrete example and go over how it's done. So if you had these two images of the same object from different poses, different view angles, you could have, once again, you extract key points, and those key points could be these lying in R D. So those are the features that are lying in R D. You have a similar set of features lying in R D for the second image. So you have that entire feature space that you divide into a grid, for instance, and now you're going to count how many of the features in one image occur in each of that grid of the feature space. That's going to define a histogram. You match the histogram at that level, then collapse the grid and merge regions in your grid in R D, in your d-dimensional vector, assuming D is the size of the descriptor corresponding to the feature. You match at that level, so on and so forth. And one intuition here is you want to give a higher weight to matches at a finer level and a lower weight to matches at a higher level where the histogram bins may be merged. We'll give a concrete example and walk over this idea. Let's consider now that you have a set of features, an unordered set of features in an image X, which is given by these blue points, a similar unordered set of features in image Y given by the red points. So remember, these are points, these are descriptors of those features lying in R D, and you're going to bin them into a very fine bin of features in that space. So it's possible that this blue point was lying in this bin, this blue point was lying in this bin, and so on and so forth. You're just binning that entire R D region into different bins, and you're placing each key point occurring in each image into one of those bins based on the descriptor values. Now you have 1D points, it's XY, on grid of size 1. We're going to call it size 1. This is the finest resolution. So now we define histograms. So your level 0 histograms are going to be this particular bin in your R D grid has one feature. This particular bin in R D in X has one feature. This particular bin in R D has one feature in image X and one feature in image Y, so on and so forth. So you can construct your histogram. Obviously, it's possible that you could have one more feature here of Y in the same bin, but at the first level, we create these bins in such a way, or you can always define bins at a very fine level. You create these bins in such a way that there's only one feature in each of the bins. We'll obviously merge these as we go to be able to combine them in a more effective manner. So based on these histograms, when you try to match them, remember our histogram intersection is going to be the min of each element. So you're going to be left with the intersection, which is simply one value here for this bin and one value here for this bin. All of the other bins have one of the elements in X or Y to be 0, which means they'll get removed. So you have two matches now between images X and Y, and you're going to weight them by a value 1. So your total similarity score now is going to be 2 into 1, which is 2. Now we're going to merge your histogram bins. Originally, if you had, say, about 20 histogram bins, you're going to merge every contiguous one and make them into 10 bins. And now you see that it's possible that there are two features in image X that belong to the same bin, and so on and so forth. So now we construct what are known as level 1 histograms, where we count the number of features in each of these merged bins in image X and image Y. You see that there are two occurrences of features in this bin. Similarly, there are two occurrences of features in this bin in image X, but image Y has just one feature still in each bin. So based on that, we build the histogram for image X, build the histogram for image Y, and now you compute the intersection of these two histograms, and you find that there are 4 matches. But you do not count all the 4 matches, you count how many new matches are added. So we are only going to look at how many new matches are added by matching these histograms, which is going to be, we had 2 matches earlier, we have 4 matches now, the new matches would be 2. So now you consider those new matches, you weight them by half. Why half? Remember, a match at a coarser level is given lesser weight than a match at a finer level, because a finer level match means a closer match. So you take these 2 new matches, weight them by half, and now your similarity score becomes 2 into 1 from the earlier slide plus 2 into half, which is totally going to be 3. Now we continue this process. You now make your histogram bins just 5 in number, which means the number of features that you're going to have in each bin is going to increase. You can have now say 3 features in this bin in image X, so on and so forth. Once again, you can get the histogram for X, the histogram for Y. You compute the intersection, which is now going to give you the number of matches to be 1 plus 2 plus 2, which is going to be 5. But you already had 4 matches in the previous level, so the number of new matches is going to be just 1. So new matches here is going to be just 1. So the similarity score now is going to be given by 2 into 1 plus 2 into half, which was from the earlier 2 slides, plus 1 weighted by 1/4, because you're reducing the weight even further when you go to an even higher coarse level. So your total similarity score is 2 plus 2 into half plus 1 into quarter, which is going to be 3.25. So let's try to put this together. So given a set X, which consists of n different features, each belonging to R power D, let's assume that the distances of those elements range between 1 and D. This just helps us build your bins for constructing the histogram. Once you know the maximum distance between elements, you can play around with your histogram bins to define them accordingly. So we're going to define Xi as a histogram of X in R power D on a regular grid of side length 2 power I. So we start with histogram at level 1, histogram at level 0, level 2, so on and so forth. Technically speaking, we're going to start I at -1, but at -1 there are no matches. It's purely for mathematical convenience, as we will see in a moment. And then we keep building the number of histogram levels until log D, where remember D is the maximum distances between the elements. So now, given 2 images with descriptors X and Y, we're going to define formally the pyramid match as K delta XY is given by, once again, the normalization functions, summation I going from 0 to L, L being the total number of levels that you're going to build. And for each level, you're going to weight it by 1 by 2 power I. When I is equal to 0, the weight is 1. When I is equal to 1, the weight is half, so on and so forth, which we just saw in the examples on the previous slides. And at each level, you're going to count the number of new matches. The first term counts the number of matches at this level. The second term counts the matches at the previous level, and you're going to keep building that. So at each point, this is going to refer to the number of new pairs matched. So this difference can also be written, the summation of differences rather, can also be written. It would, if you expand this, you would get a telescopic sum, because you would have, when I is equal to 0, you would have 1 by 2 power 0 into kappa hi x0 y0 minus kappa hi x minus 1 y minus 1, which you ignore. That term is something that you ignore. Then you would have plus 1 by 2 into kappa of x1 y1 minus kappa x0 y0. So the x0 y0 terms will be common between these two elements, which will keep getting telescoped. So if you put them all together, you would find that the telescopic sum can be written as 1 by 2 power L into kappa of XL YL, which will be at the highest level, plus All of the other terms will get, so for example, let's take one particular example. If you take I is equal to 1 and I is equal to 2 and I is equal to 1, you're going to have 1 by 2. For simplicity, we're just going to write it as kappa x1 y1 minus kappa x0 y0, and at I is equal to 2, you're going to have 1 by 4 kappa x2 y2 minus kappa x1 y1. So this half into kappa x1 y1 and quarter into kappa x1 y1 will get subtracted, and you'll be left with quarter into kappa x1 y1, and that's what you're writing it out here. So which means x1 y1 would have only quarter left because one of them will get cancelled, so you'll be left with 1 by 2 power I plus 1 kappa of xi yi. Okay, so it's just a simplification of the telescopic sum that we see in the above equation. So this is just a mathematical representation of the example that we just saw over the last few slides. Now it can be shown that this k delta function that we just defined actually happens to be a positive definite kernel. Okay? Remember again, if you recall your discussion of kernels in support vector machines and machine learning, you will recall that a positive definite kernel has benefits because it satisfies the Mercer's theorem, and the computational efficiency increases if your kernel satisfies this property. Let's see how that holds here. Recall now that k delta is written as a weighted sum of kappa hi terms with non-negative coefficients. What are those non-negative coefficients? 1 by 2 power I. Those are non-negative coefficients. And then you have a weighted sum of different kappa hi terms. Okay? This is the terms that we are referring to. That's what k delta is. Or if you look at either of these equations, it's simply a weighted sum of kappa hi's. And we also know that each of these kappa hi's, which is your histogram intersections, is simply a min of values in each bin. So it's a summation of min terms. Now we know that min can be written as a dot product. How? If you had a number 3 and if you had a number 5, I can write 3 as I put 1 1 1 for the first 3 values and then 0 0 0 0 0, okay, assuming I can go up to value 8. Similarly for 5, I have 1s in the first 5 indices followed by 3 zeros. Now the min of these two values, which is 3, is simply a dot product between these two binary vectors, which means I can write min as a dot product, and the rest of it now would fall in nicely because a sum of dot, you would have min to be a dot product. The sum of min terms can also be written that way, and a weighted sum of such kappa hi terms with non-negative coefficients can also be written this way, which means you can write your entire k delta as a positive definite kernel. In case there are parts that are not clear to you, please go ahead and read the pyramid match kernel paper to be able to get a better sense of this. So one question here is, we just said here that min can be written as a dot product by writing out each of the numbers that you have there in this form, right? If you wrote out each of those numbers in this particular form, then min becomes a dot product. So you could ask me the question, you simply extrapolated the dot product to a sum of min terms and then sum of the min terms to a sum of kappa hi terms with non-negative coefficients and concluded that it's positive definite. Then what would be the representation of the elements on which k delta is a positive kernel? What would be that embedding? For min, the embedding was writing it out in this manner, writing each number out simply as an enumerative, in an enumerative way. What would be the corresponding embedding on which k delta becomes a positive definite kernel? To know what the embedding is, let's try to analyze this a bit more carefully. So if you had two images x and y, for convenience, let's assume that x has a lesser number of features than image Y. Remember, both of them are unordered set of features. It could be the other way too. This is without laws of generality. In that case, it would just be flipped, but otherwise you can assume that one is less than the other in terms of cardinality of features. And let's define a function pi that takes us from image X to image Y in such a way that pi is 1 to 1, which means for every feature in image X, you find the closest feature in image Y. In that case, the optimal pairwise matching would be given by, you take a feature from image X, you find the corresponding closest feature in image Y, you take the L1 distance between these two features, and you're going to find the pi, or the function that takes you from image X to image Y, which gives you the least which maximizes the reciprocal of this distance. Remember, reciprocal of the distance is going to give you a sense of similarity because it's the reciprocal. You want to find the function pi which gives you the maximum such distance. For those of you who are a bit more familiar with distance metrics, you would find that such a representation is similar to what is known as the earth mover's distance, which is given by minimum over pi x minus pi x L1 norm. Remember that this is a distance metric, while this representation of optimal pairwise matching is a similarity measure, which is why you have a max here and you have a min here. Remember that distance and similarity are complementary ideas. If one is high, the other should be low, so on and so forth. So it happens that defining X the way we did, where we defined in terms of grid locations and histograms and so on and so forth, and taking a one norm between those intersections actually gives us the embedding. For more details of this could be a bit mathematically involved, but for more details of this, please see this particular paper called Fast Image Retrieval via Embeddings. But the core idea that you want to take away from here is that the pyramid match kernel defines a positive definite kernel, which makes it efficient, because we know that a positive definite kernel that satisfies the Mercer's theorem has a certain benefit in computations using the kernel trick, and also that the embedding that corresponds to the kernel comes from can be related to the L1 distance between these X values, and this particular paper describes this in more detail. And remember that once again, pyramid match kernel is a similarity measure as any other kernel functions, and it does not penalize clutter except for the normalization. Right? By that, what we mean is it's possible that many features could be congregated in a certain section of your entire RPAR-D space, and you're not going to penalize it because that would just increase the histogram intersection count in a particular bin or so on and so forth. There's no penalization for that. The only penalization that you could have is the normalization factor that you may be having here in your kernel definition. One could extend this. Instead of dividing RPAR-D into a uniform grid where you count how many features are lying in each of that RPAR-D grid, you could also cluster all your features and now do it based on a vocabulary. So you could construct your entire histogram based on, until now in the method that we discussed, the histograms need not have been based on a vocabulary. They could have just been dividing your entire RPAR-D into several bins and counting how many features occurred in each of those grids. But you could also consider clustering your key points into a vocabulary and then building your bins based on those cluster centers. This would simply be an extension of the method that we have so far, where we would replace the regular grid with, say, hierarchical or non-hierarchical vocabulary cells. And compared to the vocabulary tree earlier, at the beginning of the last lecture, we talked about how hierarchical k-means can be used in bag of words. And we said that one of the concerns there is no principled way of giving weights to each level in the tree. Now, in pyramid match kernel, we actually have a principled way, which is given by 1 by 2 power I. Even here, the approximation quality can suffer at high dimensions simply because of the curse of dimensionality and how distance get distorted in higher dimensions. One could extend this idea of pyramid match kernel to do a pure spatial matching approach. So far, we talked about dividing. You take all the features from different images and you divide entire R par D, which is the d-dimensional descriptors for the features, into grids and then build your histograms. But you could also build these histograms on your image space. In this context, what you would do is, let's say you have in an image such as this, where a person is performing a certain action. You could divide the image into 4 parts, into 16 parts, and so on and so forth. And you have 2 different images. Now you can do matching based on histograms. How many points belong to this bin? How many points belong to the top right bin? So on and so forth. Clearly, in this approach, you are only considering the coordinate locations of the features. You are not considering the descriptor or the appearance of how that feature looks at all. But this approach could be used in trying to match, say, a person's position, or how different a person's position was with respect to an earlier position, so on and so forth. So this can be used, but has its own limitations, because in this case, you're simply counting how many the histograms turn out to be in the spatial image space, dividing the image into parts, rather than taking the descriptor of the key point and doing the histogram in the descriptor space. Okay, so you're only considering coordinates here, or the geometry of the points in the image, rather than how each of those key point appears. You could also combine these ideas to perform what is known as spatial pyramid matching. This was an extension of the pyramid match kernel. In this context, what you can do is you have a level 0 again, very similar to pyramid match kernels, where you take a set of a vocabulary, you cluster all your features into a vocabulary, and then you count how many points belong to each of these cluster centers, and you would get, say, histogram bins such as these. Now you divide your image into 4 parts, and now similarly get a histogram bin for each of these visual words for each of these segments. For the top left segment, you would once again get a histogram of 3 bins. For the bottom right segment, you would get a histogram of 3 bins, so on and so forth. So the 3 bins come from the vocabulary guided pyramid match kernel, where instead of dividing your descriptor space into uniform bins, you build cluster centers similar to bag of words, and then you count the number of features belonging to each of those visual words. You can once again divide the image even further. Now you're going to get even higher number of histogram bins corresponding to each of these locations. So in this case, your kernel is going to be, you have your pyramid match kernel, but you're now going to do that for each part of the image and add them all up. So the pyramid match kernel still exists for each part of the image, and then you keep doing this over different parts of the image. So one could look at it as a joint appearance geometry histogram. So pyramid match kernel was a pure appearance histogram because you were building the histograms in the descriptor space. We saw an example of how pyramid match kernels can be brought to spatial matching, which was a pure geometry histogram, and spatial pyramid matching brings these two together to create what are known as appearance geometry histograms. So these are robust to deformation, not completely invariant to transformations, but fairly robust to deformation by simply the process that you're defining, where you're considering the appearance as well as where each of these features occur in a given image, which was not there in the pyramid match kernel at all. So this can be used for global scene classification, where a different organization of objects should not distort your final result. A last method that we'll talk about in this lecture is Huff pyramid matching, which is clearly an extension to Huff voting, if you recall. So in this method, the idea is Remember that in typical pyramid matching, you would take a set of features and match them to features from another image. And you could do this in a fast manner by using image pyramids. If you recall discussions in earlier lectures, where you first do matching at a coarse level, then do finer matching at a deeper level of the pyramid, and so on and so forth. So you could have a bunch of correspondences which you get from matching at the level of key points. And what we're going to do now is work with these correspondences instead of two sets of unordered features. So you have a set of correspondences that you already get by doing fast pyramid matching. And remember, the central idea of Huff voting is each of your correspondences votes for a particular transformation, or you have a hypothesis of transformation based on, say, rotation angle or scale or translation, and each of these correspondences votes for a particular hypothesis, and we are now going to build histograms in that transformation space. Let's see an example here. You could assume that a local feature P in image P has a certain scale, orientation and translation to it, position to it in this particular case. So which is given by this transformation matrix. Remember that this transformation matrix is just a different way of writing what we saw earlier, where we saw you have r cos theta, r sin theta, minus r sin theta, r cos theta, tx, ty 0, 0, 1, which constitutes an affine transformation where r is the scale, theta is the orientation, and tx and ty are positions. So this is just a concise way of writing such a matrix. So these two zeros correspond to this zero vector here. One is there for mathematical simplicity, and then this sp, rp correspond to the scale and orientation of that point p, which can be written as a 2 cross 2 matrix, and this vector t of p corresponds to the position of that particular point in the image. Assuming this is how a local feature is given to us, then a correspondence between a pair of features p in p and q in q can be given by fc is given as fq into fp inverse. Okay, remember fp is one point p's representation. Similarly, fq would be the point q's representation in image q, and the correspondence between these 2 points is given by scrc tc01. Once again, this boils down to your rotation and scale matrix coming here, your translation tx ty coming here, and your 0, 0, 1. Now tx ty are not just the coordinates, they are how much you moved from the coordinate in image x or point p to the coordinate q in image q. And similarly, the scale and the rotation tells you what is the transformation, how much did you rotate to go from image p to image q, and how much did you zoom in or zoom out to go from image p to image q. So tc, so we are not going to go deeper into this, but just to complete this discussion, this tc can be written as tq, which is the coordinate location of q, minus scrc tp. Why is that so? tq is the position of q in image q, tp is the position of point p in image p, and scrc says how did you rotate p and how did you zoom p to get to a point in image q. And the difference between those two locations is going to be the actual translation tc. Similarly, you can define the relative zoom in or zoom out to be the scale in q divided by the scale in p, and the rotation similarly to be given as rq into rp inverse, or the angle is given by the orientation in image of point q in image q minus theta of p, the orientation of p in p. This is how a correspondence is given. So now let's come back to Huff pyramid matching. So which means the transformation can be given by a 4D vector t of c, which has tx and ty, s of c, the scaling factor, and theta of c, which is the orientation or the rotation difference. So we're going to define one more thing before we go into the Huff pyramid matching, where if you had two correspondences PQ and P prime Q prime, we say that these two correspondences are conflicting if either P is equal to P prime or Q is equal to Q prime, or rather if 2 points from image P match to the same point in image Q, or 1 point from image P matches to 2 points in image Q, you call such correspondence to be conflicting. We're going to see how to use this when we go to the next slide. So let's see how the Huff pyramid matching actually works. So you have a set of correspondences now which are laid out in your 4D space. Remember, each correspondence has Tx, Ty, S and theta. So in this 4D space, you're going to have each of these correspondences laid out. Now you should be able to draw similarity to the pyramid match kernel, because now you're going to be doing all your pyramid matching in this 4D transformation space, and that's why we call it Huff pyramid matching. So each correspondence C is weighted by some W of C based on some, say, visual word. You can choose to use this, or you can have a uniform weight if you choose. Then at level 0, which is the first level of matching, remember, where you have very granular bins, if there are conflicting correspondences in the same bin, you're going to erase them. For example, you see that C7 and C8 have two different points from image P matching to the same point in image Q. So you're going to remove one of them. So C7 is removed in this case, and you retain only C8. Now in each of these bins in this pyramid, remember this binning now is in the transformation space again, right? That 4D space of translation, scale and rotation. So in each of these bin B with, say, NB correspondences. So for example, this bin you have 2 correspondences, this bin you have 3 correspondences. So each correspondence groups with 2 others, right? In this case there are 3, so each correspondence groups with 3 others, and your weight at level 0 is going to be 1, very similar to how we did it for pyramid match kernel. So now if you see here, you see that you have the similarity scores now, which is given by, you have for C1, which is here, you have 2 new points or 2 new correspondences that it gets combined with, so you put the score to be 2. For C2 similarly, you have 2 new correspondences, so you put the score 2. For C3 you have 2. For C4 you have just 1 new correspondence in addition to C4 in that bin, so you put a 1. For C5 you have 1 new correspondence in that bin, so you put a 1, so on and so forth. So you see that for C6, C7, C8 and C9 there are no new correspondences. You assume now that C9 belongs to the next bin, so it doesn't correspond there. Okay, so that's what you're not going to count that here. So you have, those are the similarity scores that you're going to have for this level. So when you go to the next level, you merge those bins. Now you're left with just a 2 cross 2 gridding of that transformation space. Okay, once again now you're going to erase all conflicting correspondences. Once again here you see that in this bin that C7 and C8 are matching to the same point, so you're going to remove one of them, C7 again. Now in each of these bins you count the number of new correspondences that you have. So C1 now has 4 correspondences, of which 2 it already got counted in the previous level, so it has 2 new correspondences now, which is what you're going to define for C1. Similarly, C2 has 2 new correspondences, C3 has 2 new correspondences, C4 had 1 new correspondence in the previous level and 4 now, so which means it has 3 new correspondences. So that's the 3 that you see here. Similarly, C5 has 3 and so on and so forth. Okay. And the weight for this level is half. In both these levels, you do not count C6 because C6 had a conflict and it was already counted as part of C5, those 2 points. So you do not count C6 as a correspondence in this level. So which means only C9 is left alone in this bin and hence has no new correspondences in that group. and does not contribute to any new counts. Now when you go to the next level, where you combine everything into a single bin, you now see that each of these correspondences gets newer correspondences. Once again, conflicting correspondences are erased. So you have C6 which is erased, similarly C7 which is erased, and now you see that C1 has already had 4 correspondences and it's going to get 2 new correspondences, which is why you get 2 here. Similarly, C2 will get 2 new correspondences, C3 will get 2 new correspondences, C4, C5 will also get 2 new correspondences, and C8, C9 now get 6 new correspondences each, because they didn't have any correspondences in previous bins. Okay. But the weight for each of these correspondences, since it's at a higher, coarser level, is going to be 1 by 4. So now your final similarity scores can be given by 2 plus half into 2 plus quarter into 2 into any weight that you want to give for that particular correspondence, W of C1. You can always choose to give a uniform value for WC1 to WC5 or WC9, so that weight does not matter, or you can choose to give some weights for a given application. But this is how adding up all of these gives you the similarity scores for each of these correspondences. And now you try to see which of these gives you the highest density, because that's what Huff voting is all about, where we try to look for regions where the density is maximized in transformation space, and then that gives you an effective match. That final bin or translation scale and rotation value is the final match between those 2 points in these 2 images. So Huff pyramid matching is linear in number of correspondences, which means it makes things easier. Unlike pyramid match, where you may have to match several sets of points, you're only talking about correspondences now, assuming that points have already been matched. So there's no need to count inliers here. Every correspondence can just vote, and you can just take whichever one has the highest density. And it's robust to deformations and multiple matching surfaces, and reasonably invariant to transformations because of the way Huff voting proceeds. But one important limitation here is that it only applies to same instance matching. So once again, if you had, say, a bird in an image and 2 such birds in the second image, you would not be able to do a matching, because one bird could have matched to any of these 2 birds in the second image, which means the transformations could be very different, and one of those could cause a problem for you in your final result. Your homework for this lecture is chapter 16.1.4 in Fawcett and Pong's book, and the pyramid match kernel also has a nice project page with more details, with results, with code, with the link to the paper too, if you're interested in knowing any more about these methods.